Chapter 6.1 Vectors Lane. What is a vector? Some quantities, like temperature, height, distance, area, or volume, can be represented by a single number, like 38 degrees, 14 feet, 32 square meters. Other quantities, such as force, velocity, and acceleration, have both a magnitude and a direction. How far did that box get pushed, and in what direction? A vector is a directed line segment. If we take the ordered pair AB, it represents a point in the plane. It also represents a directed line segment, or an arrow. It has its tail at the origin and its head at point AB. The length of the arrow represents the magnitude, and the direction that it points represents the direction. A two-dimensional vector is an ordered pair of real numbers, and you write it with the triangular brackets AB. A and B are the components of it, and it goes from the origin to point AB. The magnitude is the length of the arrow, and the direction of V is the direction in which the arrow is pointing. The vector 0, which goes from 0, 0, is called the zero vector, which has zero length and no direction. We represent the vector as starting at point 0, 0 and going to a point just to make it easy on ourselves mathematically. The arrow is just a representation of the vector, showing how far it goes and in what direction. Any two arrows with the same length and in the same direction represent the same vector. We can actually have an infinite number of equivalent vectors in the plane. If we have the arrow having an initial point of x1, y1, and the terminal or ending point at x2, y2, it represents the vector x2 minus x1, y2 minus y1. Showing that arrows are equivalent. If we have the arrow from the origin to point 3, 4, and the arrow from R to point S, we want to show they're equivalent by applying the HMT rule, the head minus tail. The vector from 0 to P is represented by 3 minus 0 and 4 minus 0, which gives us 3, 4. The vector from R to S is represented as -1 minus -4 and 6 minus 2, head minus tail, which gives us the vector 3, 4. So these arrows represent the same vector and are therefore equivalent. Vector archery. See how well you can direct arrows in the plane using this vector information and the head minus tail rule. The magnitude of a vector is also called the absolute value of V. It's usually denoted by V in the absolute value bars. The magnitude is calculated from the distance formula. So if vector V goes from A to B, then the magnitude will be the square root of A squared plus B squared. Putting this into application, to find the magnitude of a vector, if we have the magnitude of V represented by PQ, and P is 3, -4, and Q is 5, 2, we would put it into this formula. The magnitude, or the absolute value of V, is the square root of x2 minus x1 squared plus y2 minus y1 squared. It's the head minus tail again. So we get 5 minus 3 squared plus 2 minus -4 squared, which reduces to 2 times the square root of 10. Draw out the vector, take a look at it, do the math, and see that you actually get 2 times the square root of 10. Now try this one yourself. The algebra of vectors sometimes involves working with vectors and numbers at the same time. In this context, we call the numbers scalars. The two most basic algebraic operations involving vectors are vector addition, which is a vector plus a vector, and scalar multiplication, when we're multiplying a vector by a number. When we have the vector addition, we add the components. Vector u plus vector v will be u1 plus v1 and u2 plus v2. And the product of the scalar and the vector is similar to distributive property. In the next slide, I'll show you an example, show you exactly how to do this. If we have the vector u being 2, negative 1, and the vector v being 5, 3, we want to find 3u plus v. 3u, 3 is the scalar. We do the scalar multiplication of 3 times u, which would be 3 times 2, and 3 times negative 1, which gives us the vector 6, negative 3. Then we want to add v. 3u plus v equals 6, negative 3, plus 5, 3. 6 plus 5 gives us 11, and negative 3 plus 3 gives us 0. Try these vector operations. If the vector u is negative 4, 3, and v is 2, 5, find u plus v, 4u, and 2u plus negative 3v. Finding unit vectors. A vector u with the magnitude equal to 1 is a unit vector. Assuming v is not the zero vector, then the vector u, the unit vector, is going to be v divided by the magnitude of v, which equals 1 over the magnitude of v times v. And that's a unit vector in the direction of v. The next slide will put that to use. We want to find a unit vector in the direction of v equals 2, negative 3. We begin by finding the absolute value of v, the magnitude of 2, negative 3, which is the square root of 2 squared plus negative 3 squared, which will give us the square root of 13. So, v over the magnitude of v is 1 over the square root of 13 times the vector 2, negative 3. 1 over the square root of 13 is our scalar. So we use scalar multiplication, and we get 2 over the square root of 13 and negative 3 over the square root of 13. Try this. Find a unit vector in the direction of vector v, which is negative 2, 5. Standard unit vectors. The two vectors I, 1, 0, and j, 0, 1 are the standard unit vectors. Any vector can be written as an expression in terms of the standard unit vector. If v is ab, it's the same thing as a0 plus 0b, which is a times 1, 0 plus b times 0, 1, or ai plus bj. Resolving the vector. Resolving the vector means finding the components of the vector. If v has a direction angle of theta, the components of v can be found using the formula v equals the magnitude of v times cosine theta. That gives us the horizontal component, and the magnitude of v times sine theta gives us the vertical component. When we're using this with a unit vector, it breaks down to the horizontal component is cosine theta, and the vertical component is sine theta. Once again, the x with cosine theta and the y with sine theta. Now we're going to find the components of a vector. So we'll find the components of the vector v with directional angle 120 degrees and magnitude of 8. So to solve it, we'll let v be the vector AB. 8 is the magnitude, so for the horizontal components we have 8 times the cosine of 120 degrees, and for the vertical we have 8 times the sine of 120 degrees. Cosine of 120 degrees is negative 1/2. Sine of 120 degrees is square root of 3 over 2. So 8 times negative 1/2 is 4, and 8 times the square root of 3 over 2 is 4 times the square root of 3. So A will be equal to negative 4, and B equals 4 root 3. Now try this. Find the components of the vector u with a direction angle of 136 degrees and a magnitude of 33. Sometimes we want to find the direction angle of a vector. If we have vector u being negative 2, 3, and vector v being negative 4, negative 1, we're going to find the magnitude and direction angle of each vector. This will be two separate problems. We're going to find the magnitude and the direction angle of each vector. We'll denote alpha to be the direction angle of u. So the magnitude of u is the square root of negative 2 squared plus 3 squared, which is the square root of 13. If the vector u is negative 2, 3, that's equal to the magnitude of u times cosine alpha and the magnitude of u times sine alpha. We only need the horizontal component. So we'll take the negative 2 and set that equal to u times cosine alpha. The magnitude of u is square root of 13. So negative 2 equals the square root of 13 times cosine alpha. Solving for cosine alpha, we get negative 2 divided by square root of 13. Then we want the arc cosine. We want the inverse so that we can find alpha. Taking the inverse, we can see that our angle alpha is going to be between 90 degrees and 180 degrees. Pretend those little quarters are degree signs. Don't know why they came out that way. So alpha is between 90 degrees and 180 degrees. When you find the arc cosine, we get alpha equal to 123.69 degrees. Now with vector v, we're going to let beta be the direction angle of v. So we want to find the magnitude of the vector. So it will be the square root of negative 4 squared plus negative 1 squared equals the square root of 17. Again, we only need the horizontal component. So negative 4, which is the first component of the vector v, will equal to the magnitude of v times cosine of beta. The magnitude was the square root of 17, so negative 4 equals the square root of 17 cosine beta. Solving for cosine beta, we get cosine beta equals negative 4 divided by the square root of 17. I'm going to do it a little bit differently than they show here in the slide. If you follow along with your calculator, we want the arc cosine. So calculate negative 4 divided by the square root of 17. Find the arc cosine, and we get 14.03624. Well, obviously, beta is not 14 degrees. Beta has to be between 180 degrees and 270 degrees. Ignore that extra 0 and the quarter there. It lies between 180 degrees and 270 degrees. So we can add the 14.036 to 180 degrees, and we get the
194.04 degrees for beta.
So, how much money are we really saving here?